Hello there, and welcome to Correlation and its Impact on the World of Statistics. Today we're going to be going over how to find the sum of the residuals squared by hand and how to interpret the slope and y-intercept of a correlative set of values. Now keep in mind here that we're not going to go too in-depth into some of the terminology, but we're going to introduce you to it. So back in your old algebra days, you were told that if you could draw a straight line, then you could find points on that line. And that line was represented by y equals mx plus b, where you should know what m and b already are. So far so good. We're going to pull back a lot on these algebraic roots, but that's beside the point for the moment. So when you're talking about correlation, we usually refer to it in terms of the correlation coefficient, where you get it bound between 1 and it's bound between -1 as well. So if you're dealing with a positive 1, then that's going back to algebra where you have a perfectly positive linear line. When we say positive, we're referring to the slope of the line because it's going up from left to right, as opposed to a -1 where you get a perfectly negative relationship, so it has a negative slope where every point lies on the line. Now, if you get an R of 0, because that's in the middle, it's going to look like just a bunch of random dots all over the place that don't seem to really match up to anything. So, in perspective, this really doesn't happen too often. Those extremes don't happen too often. What you do see is if you were to be able to draw a straight line, then you get a bunch of dots that happen around that line. And we get an R value associated with it. Now, I'm not expecting you to find it, but you do have to know that the R is kind of like a percentage, where you can talk about it in terms of the strength and the direction of the particular data set. Or you can think of it as a measure of accuracy. So in other words, the closer to 1 that you get, the better the distribution is. Now, if I was to take a bunch of green dots and put them really close to that line, not necessarily on top of it, but really close, and this would probably be an R of about 0.9, where if I was to draw a bunch of blue dots a little further out, that would probably be about maybe well, this would be about 0.95, and this would be about a 0.9. But again, these are all just estimations. These aren't exact values. So bear in mind with this that you're going to be getting R mostly from your calculators. Now, the regression often involves something called the line of best fit. So that means that if I draw you a scatter diagram, which is a bunch of dots scattered around, you should be able to draw a line that fits through half the data points. So half above, half below, with the least amount of error. And you find this line using a linear regression of ax plus b. Now that being said, you punch this into your calculator in list 1 and list 2. I'll show you, I'll go by it step by step in just a second, but you're looking for 3 outputs. So how do you do these particular functions? Step 1, you plug in your x data into list 1. Step 2, you plug in your y data into L2, and then 3, you go stat, and then off to calc, and then lin reg ax plus b. Now, if you're looking for other inputs, it's going to be for L1 and L2, where A is determined to be your slope, just like in the good old algebra days, M. B is going to be your y-intercept, and we already went over what R is. R is the correlation coefficient, which we're just going to refer to as correl coef. By the way, correlation coefficient for this line, it's definitely going to be bigger than 0 because it's going up in a positive direction when you're moving from left to right. Now, as far as this, I'd give it maybe about an R of 0.85, give or take. But let's look at some real data just for a minute after we start doing some interpretations. So when you're interpreting anything like the slope or the y-intercept, you're always referring to it in terms of its variables. So what if I give you a distribution where we talk about x being the number of drinks that someone has, and the y variable being their IQ score. Now, we can assume that the more someone drinks, the lower their IQ gets. Let's just give this a slope of about maybe -5 and a y-intercept of 130. So it'll be y hat equals -5x, whoops, not m, x, plus 130. For those of you that don't know this off the top of your heads, because this is something that you're supposed to know, the y hat is technically called the new y equals mx plus b, but y hat is going to be for predicted, not the actual y value. So far, so good. So our interpretation as the amount of drinks someone has, amount of drinking someone does, I'm not going to write out the full thing, increases by 1, then the person's IQ also decreases by 5 points. Simple enough interpretation, just requires a lot of fluff, so you really have to read into the question to figure out what you're looking at. That being said, the y-intercept is a funky item because it may not be appropriate to interpret it, because it assumes that the x value that we have here has to be 0 or non-existent. Well, if it's non-existent and it doesn't make sense to the y variable, what's the point? It's like saying have a car that is 0 pounds gets 65 miles per gallon. Great, you show me a car that's 0 pounds and I'll show you a car that's got 65 miles per gallon, right? Got to keep it on Earth, folks. So, more importantly, there's another value here called the coefficient of determination. There's a specific definition for it in your textbooks, but I personally like to call it the percentage of the blame that can be based on the line itself. So an r squared of about 90% usually means that 90% of the blame is on the linear regression or the relationship between the two variables. But we're not here to talk about coefficient of determination. I can go on and on about this. So a residual, observed minus expected, where the y values are the observed and the y hats are your expected values. Your observed values, these are given to you. And they're usually given in terms of x's and y's, kind of like the ordered pairs from the days of old. How do you find y hat? It's equal to ax plus b. And how do you get the ax plus b? We find that through linreg. Ringing any bells? Good. So a residual squared, don't get this confused. A residual squared is just the residual value from the previous page squared. But don't get it mixed up with -1. Actually, let's use a different residual. Let's use -5 squared versus -5 being squared. Do not get these two values confused. This is most likely the residual. This is not, because residuals must always be positive. So how to find the residual squared by hand? Now, some of you have been asking me, how do you do this? What's the point behind this? The point of finding the residual squared leads you into hypothesis testing for regression, something that's going to be on most of people's finals. Now, whenever you're making out your chart, and I'm going to give you these values, but you need x, y values, those ordered pairs we were talking about a second ago. So I'm going to give you an x and y with a positive linear relationship. How do I know? I made the data. But if you don't know how to find it, well, we can punch in the data into L1 and L2 and find a linreg. Now, I punched this data in and I got an A of about 1.4, a B, I believe, of 1.8, and an R of 0.8682. Now, keep in mind, this is a pretty good relationship. But we plug in everything accordingly. We get our y hat equals 1.4x plus 1.8. So now we need to find our expected values based on the slope and the y-intercept. How can we do that accordingly? Well, we're going to fill it in on our chart, and we're going to plug every single x value that we have into our expected value equations. Now, this being said, you're going to take that x equals 1, plug it in, and you should get an expected value. You're going to do the same thing again for 2, and for 3, and for 4, and for 5. So I'm going to slow down a little bit, and I'm going to let you guys see how we're actually writing this out piece by piece. There are ways to do it in list functions. If people ask, I will show them. But that's not what I'm trying to focus on here today. Because take a look at the expected values as they're coming out. Because can the expected values be higher or lower than whatever we're getting? Absolutely. It's a matter of using that to your advantage to finding the residual. So all our equations are set. We have our 1, we have our 2, 3, 4, 5, and these are our expected values. Okay, food for thought, just keep that in mind. Now experience values, expected values. Well, now we need to find our residuals. Okay, so we take our observed minus the predicted. So the 3 minus the 3.2 accordingly. And the 4 minus the 4.6 accordingly. And we want to keep going down this trend, but you want to make sure of a couple of things, and I'm going to name these off while we're writing this out. The residuals can be positive or negative, but you don't want them all to be all negative, and you don't want them to be all positive, because all negative means that your line is too high. All negative means that your line is too low. Now, when you punch things into linreg, it eventually brings out the best line, meaning that it has the least amount of error possible. Keep in mind, I botched my 2 the first time around, so I apologize, so it's overwritten one on top of the other. Bear with it. Ooh, excuse me, that was a good dinner. Anyways, so now we found all our residuals, and we're literally going to square them. And I mean that quite literally. We're going to take that negative 0.2, and we are going to square it. We're going to take that negative 0.6, square it. So, as observed, and we are going to square the crackers out of everything. And all these numbers are going to come out positive if you do it correctly. So, just keep that in mind. Also, when you're showing your work, notice how I'm purposely leaving in a couple of negatives and purposely leaving in a couple of positives. Make sure that you keep track, because the residuals are not going to counteract the effect. The residual squareds are not going to counteract the effect of the positives and negatives. So you can have a completely correct residual squared, but you may have an incorrect residual, and that's just because you didn't keep track of your negatives. Notice how a couple of these are starting to fill into positives and negatives? Yep. Got to keep track of that. Now you're going to add everything in the last column, and what do you get? The sum of the y's minus the y hats squared equals 6. Done. Now, wait a minute. Some of you just got blindsided because you're wondering, why do we even care about this? Well, this whole equality right here is the residual squared. We got our residuals, and we squared the crackers out of them, and we wanted to find these residuals squared on purpose for one reason and one reason alone. Because when you go into chapter 14, you're going to have to find something called the S sub E. And the S sub E is unique in the perspective that it's one of the very few equations that uses this particular terminology. The sum of the residuals squared, see if I can write this properly, residuals squared over n minus 2 degrees of freedom. So that's the purpose behind this particular video and why it's important to know everything starting from correlation going up to residuals. You can't do a residual squared without having the residuals. You can't do a residual without having your y hat. You can't have your y hat without having your r, and you can't do your r without having x and y data. I hope this was enlightening for you. I apologize for the length of this video, but we did do it by hand. More on this as it develops.